Greetings, fellow learners. In this video, we're going to talk about backpropagation. So in our last video, we looked at multi-layer perceptrons and mostly asked the question of why do we even need backpropagation? And the answer to this is that in our multi-layer perceptron, which has multiple layers, we add multiple layers of non-linear units so that we could recognize more complex patterns. Now, these non-linear hidden units are supposed to be good feature detectors, and they have to learn to be good feature detectors. And what this means is that these edge weights over here that connect or input to these hidden units should also be learned as well. And the perceptron convergence learning procedure, which we had typically used in the perceptron architecture, cannot be used to learn the weights of all layers. And to understand exactly why this is the case and why it can only learn the weights of this last layer and not these other layers, I encourage you to check out that previous video. Now, because it can't learn the weights of all layers, it necessitates the need for a new learning procedure. And the new learning procedure that we even use until today is the backpropagation of errors. So, some questions that we are going to look at in this video is, for one, how did backpropagation evolve to be what it is today? And two, towards the end of the video, we're going to look at a little bit of an exposition about who invented backpropagation, a deceptively simple question with an extremely complex answer. So let's get to it. So in order to describe the evolution of backpropagation, let's now consider a very simple equation. We have y is equal to a0x plus a1. X is the input, y is the output, a0 and a1 are parameters. And let's say that we make a bunch of observations of x's and then we record the output y. Now the goal would be to find these parameters a0 and a1. So how would we do this? Well, in this case, there are observations which we can plug into this equation. So there's more equations than there are unknowns, and we can easily solve for a1 and a0. So the method that we use, whether it's method of substitution, elimination, these are analytical methods. Now, unfortunately though, analytical methods are not very practical for more complex cases. Now, let's go to the first person in our story, who's Cauchy. Back in 1847, he's a French mathematician who wanted to understand the orbit of planets. Now, analytical methods, though, could not really be good at solving these problems. So when we're talking about more complex problems, compared to our little simple one here, more complex problems would have more unknown parameters. They also have more observations that are being made. There's also a potential nonlinear relationship that exists between the inputs and the output. And to top it all off, there might be noise in the system, so there's no real exact solution. So in this case, an analytical method may not be feasible to solve this problem, to find the parameters that exist here. Now, in order to solve this equation, that is, understand what the values of those individual parameters could be, we could use a numerical method instead. And the general guideline of a numerical method involves 4 steps. So start with the guess, you determine the cost of the guess, you make very small nudges or changes to the parameters to reduce that cost gradually, and you repeat step 2 and step 3 until you finally reach a cost that is acceptable. Now, the goal overall of a numerical method would thus be to enable parameters to converge to an approximate solution guided by the cost. And one such numerical method that Cauchy introduced back in the 1840s would be known as gradient descent. And it kind of looks like this, where, the step one that we mentioned was starting with a guess. So let's say that the problem that Cauchy wanted to solve can be bubbled up to look like this. Specifically, we could say that, y could be the position of the planet along the orbit, since that's what he was interested in. Some parameters could be like velocity, others mass. This essentially would just be like a big differential equation. And then we have some noise in the system as well. And now we can start with a guess for the parameters a0 through an for n parameters. Step 2 is now to compute a cost of this guess. Let's just say that the cost would be the error, so the squared error of what we observe as the orbital position to what is predicted by our model for orbital position across all samples. And then what we're going to do is use this very magically looking equation to decrease the cost, where we nudge each parameter by eta times the gradient of the cost with respect to that parameter. Now here, the negative gradient represents the direction in which you want to change the parameter, and then eta represents the magnitude of what you want to change the parameter. This works because the direction of the gradient vector is the direction of steepest ascent. So just to pause and ponder, I'm going to repeat that again. This works because the direction of the gradient vector is the direction of steepest ascent. So let's get into the details of what do we mean by this. So what is this gradient vector, first of all? So this gradient vector can be represented by nabla j, and mathematically it is a vector of the partial derivatives of this j with respect to each parameter. And what we are saying now is that this vector is essentially going to correspond to the direction of steepest ascent. So if I were to say this in much simpler English, is that let's say that we have like an n-dimensional space or an n plus one dimensional space where we initialize parameters a0 to an, and that's a single point. Now, what direction do we need to move in order to maximize the change in this j? And well, the answer to that is what we're saying is that if we, nudge the parameter a0 in the direction of delta j by delta a0, nudge the parameter a1 in the direction of delta j by delta a1, so on, all the way, we would nudge an slightly in the direction of delta j by delta an, then this would correspond to the maximum jump that we could possibly make by nudging these parameters. Now, it sounds like a mouthful, but honestly, it'll probably be more clear if we show this visually with some simple examples. So let's consider this first example where we have like a very simple function j, which is x squared plus y squared. Now, if we take the gradient of this and we compute the gradient vector, it's going to be 2x and 2y. Now, what we are trying to imply here is that, let's say that we started at a point x, y. If we wanted to determine the direction of maximum ascent of j, then what we would need to do is nudge this point in the x direction by 2x and nudge the point in the y direction by 2y. Now, let's see what that looks like more visually in a graph. So I've come to this 3D plotter here just so that we can visualize what's going on. Now, let's say that our function is for this x squared plus y squared. So this is going to be like a nice parabolic shape where the z-axis is going to represent the cost, and then we have the xy plane, which represents our parameters. Now, what we're going to do here is we're going to add a vector field. And this vector field is essentially going to be for every single point xy, it's going to determine what is the direction of the gradient vector. So in this case, our gradient vector, what we want to point to is going to be 2x and to y. This is exactly what we computed by hand previously. And so if I enable this vector field to be visible, you can see that, for every single point on this curve, like if we were at this point, which is like right here on the curve, what would be the direction of the gradient vector? It would be in this outward direction. So it'll be like, it would go upwards. Similarly, if, at this point, the direction of the gradient vector is also pointing outwards here. And so on, we can see that for every single point. Now, what we claimed now is that the direction of this gradient vector actually is the direction of steepest ascent, which, if you kind of just look at this, it is true, right? Like at any point that you can see, whether it's here on the cost function, you could see that the direction of the gradient right here, it actually does correspond to the direction that you would want to go to ascend this curve. Even from here, you can actually try this out with any point. And so this vector field actually gives us a good schematic representation of, at every point, what is the direction of the derivative. And we can visually see that the direction of the derivative at any point is truly the direction of steepest ascent. Now, just to hammer home this point, let's look at another example where j is equal to xy now, and we compute the gradient vector to be yx. So to be clear, what we mean by this in English is that, if we start at some point xy, in order to get the maximum gain in j, we would need to nudge this point in the x direction by y and nudge it in the y direction by x. And if we go back to our plotter, let's actually enter this in our plotter here. So let's see now the new value of z, let's say that it's xy. Okay, let's get rid of our vector field right now. So you can see, just to visualize it, it's a little bit tilted, but now you can see in the x, y, and z direction how this kind of looks. So just before I create the vector field here, which is going to be for y and x, which is what we computed by hand just now of the gradient vector, before I enable this vector field, I want you to take a moment to see what you think the vector field is going to look like. All right, have you thought about it? Great. So let's enable this vector field and see what's happened. All right, so remember, the vector field is going to give the direction of the gradient at every single point along the xy plane. But you can also see that, if you look at this is the cost function right here, that, at every single point here, in order to go up, we can see that it's actually in the same direction as that of the gradient vector. And so we can visually see that the gradient vector once again gives the direction of steepest ascent. Now, this isn't really a proof, but it is a nice visual guide to just show that this is true. And I can link to formal proofs more mathematically down in the description below. And so what we can see here is that this delta j, delta ai, is going to be the direction of steepest ascent. And hence we take the negative of this direction because we want to go down, and descend because we want to minimize this cost. So I hope that adds some more intuition on what this gradient descent update rule is actually doing and why it exists the way it does. Okay, so this gradient descent method relies on us to compute the gradient with respect to every parameter. But this computation of the gradient can become very expensive. We have to compute the partial derivative, after all, with respect to every single parameter. So how do we deal with this? Well, we can use efficient methods to compute the gradient vector. So one such efficient method is known as reverse mode automatic differentiation, and another is the adjoint state or co-state method. So we're going to talk a little bit about automatic differentiation, and this second one has been used parallelly in the 1950s with respect to control theory, but a little bit more on that later. So let's say now we want to solve the problem of z is equal to xy plus sine x, and we want to find the gradient vector of z. So in automatic differentiation, what we would do is we would take this problem and kind of rephrase it. So let this first term be a, the second term is b, so z here, or z, is equal to a plus b, and we want the gradient of z with respect to x and gradient of z with respect to y. So from this, let's try to create this computation graph. So what this means here is that if there's an arrow from x to a, it means that a is a direct function of x. So you can see that x and y are just their own independent variables. A is now dependent on x and y, b is dependent on x, and z is dependent on a and b, which is representative of these equations. So let's just take the forward pass of automatic differentiation just to show its inefficiencies. So first, to do this, let's add a variable t here, an independent variable. It can take the value of x or y, which we will see later. So right now, x is simply going to be a direct function of t, and so is y. So what we can compute at this point is that first we can compute the partial derivative of x, or the derivative of x with respect to t, as well as the derivative of y with respect to t. No problem. Next, what we can do is we can compute the partial derivative of a with respect to t, as well as b with respect to t. Putting all of it together, we can compute the derivative of z with respect to t. Now what we can do is, like, say if t is just x, we now have a method to compute the derivative of z with respect to x. Now we can do another forward pass where t is equal to y, and then we can compute the derivative of z with respect to y. So this provides us a method to compute the gradients of z with respect to every variable. But this forward mode requires O of n forward passes to compute the gradient vector for n parameters. And this can be quite inefficient, especially for a larger number of parameters. So let's now talk about the reverse mode automatic differentiation and see how that can be more efficient. So in this case, we start from the end, whereas the derivative of z with respect to z, which is just a seed of 1. From this, we can directly compute derivative of z with respect to a and derivative of z with respect to b. Z is, after all, a plus b, so you can directly compute these two derivatives. So that's great. From this, using chain rule, we can then compute the derivative of z with respect to x and derivative of z with respect to y, as it's a function of these partial derivatives using chain rule. And so what we can see here now is that in this reverse mode, we only needed one backward pass to compute the gradient vector for n parameters. So you can see how efficient this method can be. Now, for more technical details on this and even code, I'm going to link this blog post right here in the description below, so I encourage you to check it out. Now, I guess you can see now how you can use this method in neural networks. So let's say that we have our neural network over here, where we have the prediction that's coming as the output of the neural network. Then we will now compare it to the observed value in order to generate our cost j. And you can see now from the reverse end, we can start with the partial derivative of j with respect to j. It's just 1. But we can then compute the partial derivative of j with respect to y pred. It's an easy computation. And then what we can do is continuously use the chain rule in the reverse direction, like we saw before in our computation graph, in order to get the partial derivative of the cost with respect to every single edge weight or every single parameter in the network. And all of this basically just required one backward pass to compute all the gradients. And hence, this becomes an efficient method to learn the gradient vector in a multi-layered network. And hence it could also be used in the gradient update equation pretty easily. So this here is kind of the evolution of how backpropagation came to be and how it is now more efficient. Now, the next question I wanted to answer in this video, or at least attempt to try to answer, is who invented backpropagation? Like I mentioned in the beginning of this video, it is a very deceptively simple question with a complicated answer, because backpropagation was invented multiple times by multiple people from the 1950s through the 1980s. So let's just list out a few people and where and how they kind of fit into this entire story. So we'll start in 1960 with an aeronautics engineer, Henry J. Kelly. And in 1960, he wanted to understand the optimal flight path from Earth to Mars. And in order to do so, he invented a modification of the adjoint state method, which was itself another kind of modification of the backpropagation method, as the flight path and also the constraints were differential equations. And so he needed an efficient way to solve these equations. In the 1960s also, Bryson and Ho laid out a framework to solve problems in control theory. And they also invented a version of backpropagation that could be used in controllers. Control theory is a branch of engineering that can be geared towards understanding how to create automated systems. Then we have Seppo Linenmaa. In 1970, he wrote a master's thesis that describes reverse mode automatic differentiation. Now, this was an unpublished work, however, at that time. And in 1974, we have a publication by Paul Werbis, where he published the first version of backpropagation to a multi-layered perceptron. He apparently came up with the idea almost a decade prior, but there were problems along the way for him to try to get to publishing this. In the 1980s, we saw Jan LeCun, who also described a version of backpropagation in his PhD thesis to train neural networks. But probably the most famous among all of these is the 1986 publication by Rumelhart, Hinton, and Williams. So through the 1980s, they had created a version of backpropagation that we even use today. And after this point, there wasn't really much a rediscovery or reinvention of backpropagation. They are also responsible for popularizing backpropagation in general as a learning procedure. Now, I found a really cool blog post of all of this backstory relating to backpropagation, and I'll link it down in the description below because I thought it's a super interesting read. Quiz time. Have you been paying attention? Let's quiz you to find out. What is the main advantage of backpropagation over the perceptron convergence learning procedure in neural networks? A. It could solve partial differential equations efficiently. B. Parameters in all hidden layers could now be learned, and not just the last layer. C. It enabled a multi-layer network to model complex nonlinear relationships. Or D. It provided a systematic way to minimize the overall error using gradient descent. I'll give you some time to answer this question. The correct answer is B. Did you get it right? Leave your reasoning down in the comments below and let's have a discussion. And if you think I do deserve it at this point, please do consider giving this video a like because it will help me out a lot. Now that's going to do it for quiz time, but before we go, let's generate a summary. The perceptron convergence learning procedure, which was used by perceptrons to learn, could not be used for a multi-layered architecture. And so we use backpropagation of errors. But how did backpropagation evolve to be this algorithm, and who invented it? We saw that for very complex problems, analytical solutions may be infeasible. And so, in order to solve these, we could use numerical methods instead. One such numerical method was developed by Cauchy, known as gradient descent. In gradient descent, we start with a guess for the parameters a0 to an. We then compute the cost, and we then update the parameters by nudging them in the direction of steepest descent. This delta JA by delta AI is the direction of steepest ascent. The negative sign means the opposite direction of that. And eta is going to be the magnitude of the jump. But the computation of the gradient vector can be quite expensive. And so we also discussed efficient methods to compute the gradient via reverse mode automatic differentiation or the adjoint state method. While the forward mode requires O of n forward passes to compute the gradient vector for n parameters, the reverse mode only requires one pass to compute the gradient vector for all parameters, making it far more efficient. And so this efficient computation is also used in neural networks today. We also saw that backpropagation was invented multiple times by multiple people from the 1950s through the 80s. We had a few of these cases that came from optimal control theory. We also had some coming from master's theses and also PhD theses. And then we have the most famous version of backpropagation, which was Rumelhart, Hinton, and Williams in the 1980s. That became more popularized even today. And that's all that we have for today. I hope that this video helped shine some light onto why we have this backpropagation learning procedure today, and also some of the visualizations that surround intuition of this too. So, thank you all so much for watching. Please do consider giving this video a like. All of the amazing resources for this video are going to be down in the description below, and I'll encourage you to go through them for a lot of further reading. Thank you all so much, and I will see you in the next one. Bye-bye.